why should we work in the impedance domain? And you know, basically, make sure I know how to use this. Basically, we're trying to, you know, we're trying to pull as much as we can from seismic data. So it's beyond just mapping structures. It's beyond, you know, just, you know, really simple things that we typically do. But how can we actually get rock parameters, reservoir parameters out of the seismic data? And you know, to be able to do that, seismic inversion is the process by which we can attempt to pull that information from the seismic data. And it has been described as inverse modeling because if you think of forward modeling, you start with rock properties, and from rock properties you try to estimate what the seismic or reflectivity response would be. So that's forward modeling from rock properties. So it's inversion because you're starting with the seismic data already and you're trying to, you know, make estimates of those rock properties. Of course, calibration to well control is fairly critical, just like with any seismic process. If you don't know what you're looking at, you could basically, you know, make any sort of determination. But where you have well control, it allows you to get that much more information from it. You can, you know, you may think, well, okay, I need to do inversion only for development wells or for production or something. But you can use it for the full range of activities, from exploration all the way through production work. And I just need to mention, you know, what acoustic impedance is. I'm sure most of you would know what it is, but it's just the product of velocity and density. So that's where the word impedance comes from. And when you look at reflectivity data, you're talking about the contrast in acoustic impedance. When we talk about inverted data, impedance data, you're trying to understand what those layers are telling you. So if you have two layers as shown here, and they have contrasting acoustic impedance, right at the boundary you would see a reflection. In this case, this is a lower acoustic impedance going to a higher acoustic impedance. In terms of reflectivity, if it's normal polarity convention, you'll see a peak on your reflectivity data. Okay, so why seismic inversion? It looks more like geology, so it's a great integration medium. Where I currently work, I work in an integrated R&D team, and a lot of the work that I do is in support of other geoscientists, sedimentologists, structural geologists, petroleum systems people, and a lot of times they don't just work in reflectivity anymore, but you know, we generate on a very routine basis impedance volumes. So you know, we're looking at properties of the layer itself instead of looking at the contrast in rock properties and the interfaces, which is what we see in reflectivity data. And it's easy to relate to reservoir properties. And there are some techniques that have been developed, and you know, we're continuously looking at ways of developing quantitative predictions, you know, gross thickness, net sand, net pay, etc. When you think of impedance data, also, if you think you're looking at the layers, you aren't thinking too much about the overburden, what has happened above it. You're looking at the particular layer. Another thing that, you know, this is sort of in the method of doing the inversion, you need to have, if you do have well data, even if it's offset well data, which is, you know, even outside of your three-dimensional volume, it's important to understand what those well ties are telling you. So it forces you to make those well ties. It may broaden the bandwidth, so it allows you to have higher resolution depending on the type of inversion also. And it does remove wavelet effects, which would be side lobes and things like that. So what you should be seeing depending on how the inversion is done again, would be the layers themselves, and not reflectivity that you're seeing because of wavelet effects. Okay, so if you look at reflectivity data, let's assume it's zero phase data, which means that if you have a gas sand, the top of the gas sand would be the maximum trough event in standard polarity. So if I just put a wiggle on a display on here, so the top of my sand will be this maximum trough event. The base of my sand, assuming it's above seismic resolution, would be the middle of that P. If I were to look at inverted data now, you're mapping the body, sand body, as zero crossing to zero crossing. Again, if it's above seismic resolution. And in this case, the sand is a low impedance sand. If you just look at the color bar on here, the low numbers are the red colors. So you're just mapping, if you map zero crossing to zero crossing, you're effectively mapping the layer. Whether it's, you know, if it's a brine sand or hydrocarbon sand. Okay, a method that we use at BP, it's called colored inversion, and it has been published by Lancaster and Whitcomb in 2000. They presented a paper at the SEG on it, and basically it benchmarked really, really well against unconstrained sparse-back inversion, which is, one may consider that to be a specialist type of inversion process. Whereas colored inversion, I mean, it's more of a generalist type inversion process. So it worked much better than fast-track inversions like recursive inversion or some of the shell methods, the Ramsar methods, and then the Jason methods, the unconstrained fast-back, which means you have much less well control. So it has worked, you know, it works really, really well on here. And basically what the method what it's doing, it's looking at, it's a convolutional operator, and it's looking at your seismic spectrum, your log spectrum, and trying to match your seismic spectrum, which is in the red in this case, to the well spectrum, which is in the green. So it's a matching operator, and it has a phase rotation of negative 90 degrees. Hence, we were able to, you know, in inverted data, you map zero crossings to zero crossings. So the reason it's called colored inversion is because it's boosting on the low end as well as the high end. These graphs are just graphs of amplitude with frequency. So this is just a typical amplitude frequency spectrum from seismic data. This is an amplitude frequency spectrum from a log acoustic impedance data set. So you just have you take the density log, compressional density log, your compressional log, and your density log, and you just multiply them, you get the acoustic impedance. And this is just looking at the amplitude decrease with frequency of that acoustic impedance log, and it goes all the way up to Nyquist. And so you fit the trend to here. And the operator is this blue color here in the frequency domain. This is what it looks like, and it's boosting the low frequencies and the high frequencies, hence the name colored inversion. The resulting time domain operator is just applied as a wavelet convolution to your seismic data, and you get inverted data. So typically at BP, we may do other methods which are more specialized methods, but even if you have regular migrated data, you could, with some, you know, well control, even if it's offset well control, you know, this method is fairly easy to apply. And if you have any questions on it, you can ask me later.
Can you answer?
Huh?
Are you allowed to answer?
I may not be able to, but unless I hear the question. So. Okay, as an input to the inversion process, whichever process you're using, it's important to have zero phase data. Now, zero phase data is not physically realizable. It's something we do to the data to have troughs, maximum troughs being tops of gas sands, maximum peaks being bases of gas sands. So, you know, this is just basically a scintille display showing that for the range of frequencies I have in my data, again, this is just a simple amplitude frequency spectrum. You know, approximately zero phase for both these examples. So on approximately zero phase, I'm happy, you know, I can proceed with inverting the data. If I were out of phase at all, significantly out of phase, I would probably zero phase my data just by, you know, doing a phase rotation phase. Okay. I just wanted to show some examples. I don't know whether you can see that, but this is reflectivity in this case, and let's assume it's above seismic resolution. So in the middle of that strong trough is the top of my sand, in the middle of that strong peak is the base of my sand. And for a peak in the impedance domain, and this is just full stack impedance I'm showing you. You know, the top is just zero crossing, and the base is just zero crossing. This one is like a channel system. So in this case, this is just reflectivity again. You have just, you know, regular mapping on conventional reflectivity data. And this is impedance. So you're actually mapping zero crossings to zero crossings where you can map out bodies, whatever they may be, whether they're hydrocarbons or brine sands or whatever. Okay? Okay, so this is just some examples of full stack inversions with well ties. One question that I can't answer is where these examples are from. So if you ask me, unfortunately I won't be able to tell you. But if you look at the color bar on here, again the reds will be your low impedance zones. So if I were just to focus on this sand here, this well, the position of the well is shown. I've put the gamma ray log on here. So, you know, that's the top of my sand there and that's the base. So it's really a nice time. If you look at this sand body in here, it's a little bit ratty. It's, you know, you have some shale breaks and so on in here. And you can see that showing up in the impedance data. One thing that you sometimes see is that you do see, even if you have a very thick, blocky sand, you do sometimes see what we call a belly. It's just, if you think about it, I almost have to draw it, but it gets back high in impedance again, just because if you don't have full bandwidth, meaning if you don't have all the way up to zero frequency and up to Nyquist, you can have a dim zone even in the middle of a good sand. And the way to correct for that is to broaden your bandwidth as much as possible, which means you increase your highs as much as you can, increase your lows as much as you can. A lot of times people think that seismic resolution increases only if you increase your high frequencies. But really, you need to increase the highs as well as the lows. The lows are equally important in allowing you to see everything in the data. So this is almost hint of what we call a belly inside here. And here you can see there's somewhat of a shale break in there trying to show up. So it's, you know, a very, very good tie to the, you know, from the gamma ray log to where the sands are in the data. Next one. Okay. Just focusing on the sand again here, you can see it's a really good time, top of the sand, base of the sand. You know, if you see something like this, you may say, well, that's questionable. I don't know what kind of quality I'm seeing there. So really, you actually, that's why we can relate now, looking at this impedance data set, you can relate what you see in terms of amplitudes, thicknesses, and so on to the sand body. It really ties very, very nicely. And the full stack inversion is just regular migrated data with as much angles as you have, as you've acquired. If you think of offsets, you know, if you just if you just look at a CDP, a common depth point gather, you start at normal incidence, and then you increase your angles. So this full stack here is just all your angles summed together. That's what it is. And it's just an inversion of a full stack data set. I just zoomed in here a little bit just so you can see again, really, that looks very nice. You'll say, well, maybe it's telling me about the quality of the sand, and it's probably telling me something about the fluid also, and how can I pull those pieces out. Okay, this is probably my main area of interest, which is AVO in the impedance domain. So typically we think of AVO, but we think of it in terms of reflectivity. So, standard reflectivity data, but there's so much more that you can pull out if you look at amplitude variation with offset in the impedance domain. And there's a lot of published work on this. Okay, amplitude variation with offset. So now Zoppert's equations, they're very, very complicated because they have so many parameters. But a lot of people have approximated his equations, and Shui is one of those who established a two-term approximation. And this is saying that reflectivity, P-wave reflectivity, is a function of an intercept term as well as a gradient sine squared theta, where that theta is your offset angle. And so Zoppert's equations relate reflectivity to angles of incidence at non-normal incident angles. Typically we think everything is going down normally into the earth, but it isn't. There is some variation of amplitude with that variation in angle. He also describes transmission, but I'm just thinking reflectivity right now. So A is normal incidence reflectivity, which is the intercept from this equation here, this two-term approximation of the Zoppert's equations, and B is the gradient too, so that's the B here. If you think about the CDP data, I have one from real data here, and one from an offset synthetic I've generated. So if you think about it, this would be my near offsets, close to normal incidence, and this is when I'm increasing my angle, this is where I'm going. Out in this direction. These are what we call my far offsets. And the real data, you can see them here too. This is, normal incidence or near offsets. Again, far offsets. So what we do at AVO is look at this variation with your offset. So you start, like for example, in this case, you're starting off fairly bright. It's a negative impedance contrast, or you're going from something that's higher acoustic impedance to something that's lower. And if you look at it carefully, it's real data, so you have to look at it carefully. I'm actually increasing or becoming more negative as I increase that angle. You can see it on the synthetic data also. It almost looks like it's really high here, and it's increasing a little bit. The thing about it though is that the frequencies also change. So when you're processing data for AVO, you have to take all those things into consideration. So you take all those amplitude values along here with your offset. So this is offset in this direction to the right, and you're plotting these amplitudes or reflection coefficient as a function of your offset angle. And this value here is the intercept value, and of course the gradient for a two-term or linear approximation is just the gradient of this value. And what we do is that we look at all these gathers and we process them. We take all these intercepts for all these gathers and we generate volumes. And the ones with all the intercept points are called an intercept volume, and then the ones with all the gradient points are called a gradient volume. So those are some of the key volumes we generate when we do AVO processing. Intercept volumes and gradient volumes. And they go all the way back to the Zoppert's equations, the two-term approximation. Okay? Okay, AVO classification based on Rutherford and Williams. Top of sand response. So you because you can have a response at the base of the sand also. So we're just looking at the top of the sand response, and typically, fairly shallow in the section. I'm thinking Trinidad, Gulf of Mexico, different areas. You have what we call class 3 responses, meaning you have a fairly strong negative reflection coefficient, which is increasing or becoming more negative with that offset angle. You just look at those CDP gathers and you'll see that's just plotting up those points and, based on empirical data. And then class 1 is where you have a positive reflection coefficient on the top of your sand, and it's decreasing. You can even have a phase reversal where you go from positive to negative with offset. Class 2, you can have this is class 2P where you have a phase reversal. Class 2 is where you are fairly dim, so you may have dim P, if you will. You're fairly dim, but you do become more negative with offset. And class 4, we found that class 4 had to be added because you can have areas where you have really strong normal incidence reflection, but they decrease or sometimes they stay the same with offset. So that's typically a class 4 response. So when you hear those terms, this is what it's referring to, based on empirical data. Okay, this is basically the same thing. All I did here was, so this is the Rutherford and Williams classification of AVO top sand response. And what I did, I color-coded it so you can see which one is referring to which one. And then I put it in cross-plot space, intercept, and gradient. That's all I did here. So if you think about class 3, I have a fairly strong negative intercept, but I also have a strong gradient. Class 4, I may have a strong intercept, negative reflection coefficient, but I may not change very much, or I may actually increase with offset. So I may have a positive gradient, so that's what it showed me there. So a lot of times it helps to look at this information as cross plots, so you pull out a little more information. Okay, AVO in the reflectivity domain. As I said, we typically think of AVO in terms of reflectivity, normal migrated data and so on, or angle stamps, near, mids, fars, difference volumes, things like that. If I were just to focus on this down here, now what we also do is you take, this is just based on log data here. So this is just based on log data. You take the entire log trace and you remove its in situ fluids and you replace it with brine, or you replace it with oil, different APIs, etc., and you replace it with gas. So you know what fluids you have in the reservoir. And for this, in this case here, this sand is showing a trough, meaning there is a negative reflection coefficient. If I fill that sand with brine, on my nares, so these are my nair traces here, these are my far traces here, and so on, near, far, near, far. So if I were to plot this response in cross-plot space here, this is amplitude versus offset. Again, this is my nares and my fars. I do have a negative reflection coefficient. It's not that strong, so I can plot it here, but I do have a negative gradient, meaning I'm becoming more negative with offset. So you can see that that's where that's plotted here. If I go for the gas case, it's a fairly strong normal incidence reflection, which is this point here, and I'm getting more negative with offset. So I have a negative gradient with offset. So I can take that information. Okay, some definitions before I go on. Okay, so AI is, everybody knows that one, implicit impedance. SI is shear impedance, which is the product of the shear velocity and the density. And some of these terms were introduced, I have some of the references on here, by several colleagues at BP in the technology group. And GI is gradient impedance, and I'll explain these a little bit more as I go. EI is elastic impedance, EEI is extended elastic impedance. And I have some references here for anyone who's interested to read further. I have those resisted at the end. And just some equations showing acoustic impedance is the product of the density and the compressional velocity. Shear impedance is the product of the density and the shear velocity. And the acoustic impedance, this is this angle, this offset angle. It's just a function of compressional velocity, shear velocity, density, and offset. And then some of these other ones introduce some other terms, but don't worry about it too much. All it's saying is that you need a little bit more information. You need like shear velocities also. You need some normalization terms, and you know typical compressional as well as density information. It's all in these equations here. Okay, so how do I go from reflectivity now to impedance? So if I go back 2 slides there, one more. Okay, so I took this information here from my log data. I plotted it up on an amplitude versus offset plot. I know what my normal incidence reflection is or my intercept value, and I could fit a straight line, probably, through there and get a gradient value. So then, if you go forward for me, I take those gradient values and intercept values and I plot them up here. And for shale, this is a shale point, overlying shale. And for my brine point, my oil point, and my gas point, I plot those up in an intercept gradient cross plot. So I went, from that amplitude versus offset picture, I just plot these values up here. And now we make the jump from reflectivity, because intercept and gradient are reflectivity volumes. They're AVO processed volumes, but they're still reflectivity volumes. And you jump across to impedance. So this is acoustic impedance, gradient impedance. So all I've done here, I've taken my intercept volume, my normal incidence volume, I invert it, and I get my acoustic impedance volume. I take my gradient volume that I've generated, and I invert it, and I get my gradient impedance volume. So that's all we've done so far. And this domain is called extended elastic impedance domain, as coined by Whitcomb et al., who published this in 2002. And what we then do is, using this information in extended elastic impedance space, is you can optimize your projection angle. See, if I were to just look at acoustic impedance data, maybe the separation between brine sands and gas sands may not be as big as it could be. So all I'm doing here is making that separation as big as it could be, generating an optimum volume to be able to see fluids. So in this space, you can generate different kinds of impedance volumes to see lithology, porosity, fluid, of course. So that's the extended elastic impedance space. This chi angle, again, if you want a little bit more information on it, I'll give you the references at the end. This chi angle is measured counterclockwise from the acoustic impedance axis. And it's 0 degrees, obviously, 0 degrees chi angle is the acoustic impedance volume. 90 degrees chi angle is your gradient impedance volumes. And again, let me just re-emphasize that it's really a straightforward process, because when we generate AVO volumes, we're generating the intercept and the gradient. You invert the intercept volume, you get acoustic impedance. You invert the gradient reflectivity volume, and you get gradient impedance. So you have these two volumes. Once you have some well data to calibrate them to, you can do these kinds of projections and optimize whatever impedance volumes you want to generate. Next. Okay, you can do the same thing in acoustic impedance, shear impedance space, and shear impedance again is just your density log. If you're thinking log data, your density log times your shear velocity log. Acoustic impedance is regular acoustic impedance, and you could do the same thing in the ISI space. Just go back a bit. What? Yeah. difficulty is that you have an additional step in going from intercept and gradient to shear impedance. If you assume your VSVP ratio, which is your shear velocity to your compressional velocity, is 1/2, it's a fairly easy process. If that ratio is anything different, then your shear impedance volume is just an approximation. It's a pseudo shear impedance volume. Okay, so this is just visualizing rough properties. So this is just log data, pure log data. In the horizontal axis, I just have the compressional velocity. And on the vertical axis, I have the depth. Unfortunately, it's increasing upwards. So if you think about it, this is your trend here with depth. And it's colored to discriminate what your gamma ray is showing. These are the low gamma ray numbers here, so related to your sands. These are the high gamma ray numbers related to your shales. So in the reds and the yellows, these will be where your sands are plotting, and the blues will be where your shales are plotting. So it's just kind of looking at the data, what is it telling me?
Is it Reeve, Rosemary?
Pardon?
Reeve?
Okay, so density with the depth. Again, depth is increasing upward, and density is increasing to the right. Color to discriminate gamma ray again, and now you can see, this is my sand trend here. My sands are always, regardless of what fluid I have in them, they're always lower density. My shales are always high density, at least for this depth of log. Okay. And this is just the product of those two, compression velocity and density. And so I've plotted P impedance with depth, discriminating. The colors are again, blues will be shales, the yellows and reds will be sands. And what I did here now is you just product of compressional velocity and density, your P impedance log, product of shear velocity and density, your S impedance log, and look what happens. You get clear separation where your shales are plotting separately from your sands. So just by looking at this data in impedance space, you can say, wow, well, I could do something here. I could produce an optimum log that is telling me sands are different to shales, and I can do the same thing with my seismic data. This is just another example showing, again, in impedance space, P impedance, S impedance. You're seeing your shales in the blues here, and higher gamma ray numbers, and the sands, clear separation between them. Okay, so just going a little bit further here. This is the natural log of acoustic impedance from log data. This is all from log data again. And the natural log of gradient impedance, which is a generated log. It's a function of compressional shear, density, and with some constants and normalization terms. You can see separations where the blue color, it's colored to discriminate V shale. So the sands in this case, I've since reversed this color bar, but the sands in this case are blue and the shales are red. So you can see, perhaps in this sand here, it may be difficult to see it. And guess what? This sand here is a brine sand. So what this tells me right away is that perhaps my shallow sand, if it has brine in it, I may not be able to see it. It might look like background shale. Whereas the deeper sand, if it's water wet, it's filled with water, I may still be able to map some amplitude, to map it out regionally or whatever else. That's what this is telling me right away. Because this is just for brine, where I've substituted the entire reservoir fluid for brine, for the entire extent of the log. And in this case here, the color discriminates V shale, and this is for the gas case. So for the shallow or the deeper sand, whatever it is, if it has gas in it, I'll see it. That's what it's telling me. It's going to be bright. I'll see a nice bright amplitude. It's going to be low acoustic impedance. You can see the blue sands here shifting to the left, which means they're low acoustic impedance. I'll see a nice bright trough on my impedance data, even if it's full step impedance data. And here I've colored to discriminate the saturation. Again, if I have gas, I'm going to see it. That's what it's telling me. And in extended elastic impedance space, what we typically do is that for a range of chi angles, I mean it's recommended to do it for negative 90 degrees to positive 90 degrees. These are not physically realizable things, they're just numbers we're playing with. Typically we generate AI-GI crosscuts and generate EI logs for a huge range of angles, and then we correlate the resulting EI logs with the V-shale log or the water saturation log or whatever you're interested in, just to show the point of highest correlation. And that would probably be an optimum angle that you would then go back to your seismic data and try to match your log to your seismic and generate the same kind of volume. And what I've done here is that for several chi values, chi equal 10, all the way up to 8 in here, and for the various fluid substitution logs, which would be brine, oil, gas, acoustic impedance as well as gradient impedance, I'm just showing, this is the sand that I'm interested in. This is just another way of describing the data that I showed in the previous crosstalks, where you have the largest separation, that might probably be a fluid type of volume, and where you have the largest kick on your brine case is probably an optimal angle for lithology. So, and it's all filtered to seismic frequencies, because obviously when we look at the log frequency, it's much different to seismic frequency. Okay, this is just another case where you can see the correlation show up a lot better. Again, this is just the log of acoustic impedance, the natural log, the log of gradient impedance here. And the reason we do the natural log is that if you don't, in AI-GI space, there is some curvature to it. But if you linearize it by putting it in logarithmic space, you can maybe get some trends that you can work with over a much larger interval. And if you're looking at a significantly large interval in your seismic data, if you have one volume that can help you a lot more than having to generate multiple volumes. So that's why we try to linearize the data sets. So in this case, for the full range of my log extent here, the blue is separated, which is the wet sand, is separated from the shale. What this is telling me is that I should be able to see wet sands in the system, whether they're, because if I want to map my sands regionally, I should be able to do it. It's not going to look like background. It's going to stand out above background. That's what it's telling me. And if I look at the gas substitute case, it's telling me that my gas sands are even going to be brighter. So I'm going to have, where this data came from, I'm going to have seismic data that is showing me some bright amplitudes where I have wet sands and brighter amplitudes where I have hydrocarbon sands. That's what it's going to tell me. And if I look here, going into extended elastic impedance space, and these are just generating all those logs that I showed you and correlating them with V-shale, clearly I can generate an optimum impedance data set for what I'm looking for. Again, a similar kind of display, and if you look on here, what I try to look for is visually, when I look at the log data, which one is jumping out at me, which one has the largest separation, which one, the brine sand, is highest amplitude. Okay, next. This is just examples of well ties. So that's my well on here. Again, the colors show red to be low impedance. So it's a class 3 type system. And I put my well ties on here. And you can see 0 crossing, 0 crossing. It's even, I could tell you that some of these are really, really below seismic resolution. But it's still trying to pull some of this information out. You're still seeing some hints of it. It's still still trying to pull out these very thin reservoirs. And yeah, I just zoomed in to show you that it matches really nicely to data. And this is just a QC check that I do when I generate a lot of these volumes and trying to put, make correlations and whatnot. So these are just a range of different impedance data sets I generated from seismic data now, and I extracted these traces from around the borehole, and I'm just trying to look and see which one is correlating best with gamma ray. Because typically what you find is that even though when you look at the well data, you may get an optimum angle that optimizes what kind of impedance you're trying to generate. When you go to the real seismic, you still need to verify and calibrate and do some QC checks. Okay, and forgive the white boxes, I had to cut off the wells. So you can do anything that you typically do with reflectivity data, you can do it on impedance data. This is what I'm just trying to share here. Generate amplitude extractions, whatever you do, typical process. Okay, so I just have a little bit of a movie here showing you. Can you just run it over? Okay, so I'm starting with just acoustic impedance and shear impedance and depth. I'm just rotating it. So this is what we're doing. We're just rotating the data. Can you go back one? I think I animated it. Go forward. Yeah, I have to stop the animation.